So the title I gave was something in thinking about where we've been in the research in looking at climate and where we're heading. I immediately thought of, my goodness, this is getting really awkward. No, there was an MP3 already behind there. There it is. Yeah. Well, this is one of my favorite albums of all time. Yeah, well, that's not going to happen, for your sake. But I was just going to play the music of The Day Begins, which is the beginning of Days of Future Past. But the title also relates to an X-Men movie, which is also called Days of Future Past. And in some sense, as I thought about climate, and really kind of, that was probably more relevant. Let's just go to the, oh, there.
There's a volume control on the top of the window. You can turn it up.
That's probably the best we can do. So, but that doesn't matter. I just had it in there for fun anyway. Let's go back to the slides quickly. Let's just go to the slides. There we go. So I did ask Catherine Hayhoe to be co-author of this talk because Catherine couldn't make the meeting. Catherine's my former student. She's been getting a lot of attention lately and was named to the Time Magazine's 100 Most Influential People in the U.S. because of the work she's been doing on climate communication. And she and I still collaborate a lot as well in research. And so I thought it was pertinent to at least include her here. She couldn't make it because Texas Tech starts school this week and she has to teach on Wednesday. So if we could go to the slides. Well, that's what the intention was, to have it just kind of back there at a low level, but technology. Yeah.
You have 1 more minute.
Yeah, that's what I'm afraid of. So, I've already talked about my past connections with, I hope I get all this back, with AGCI, and as many have expressed, I can't say enough about what this organization and John has done towards helping us look at science in a different way and connecting better across communities. In my own sake, I've worked many different issues because I just can't stay on any one topic, I think is my main problem. As I was thinking about this talk, it did occur to me that 25 years ago, just about the time I was being asked to go to that first meeting, which I still don't know why I was invited, but it was great, and I very much enjoyed it. I got asked by DOE to produce a graph about climate chemistry interactions. They couldn't understand how chemistry can influence climate, and they wanted a flow chart. And then some people still don't, obviously. But, and so I came up with this, and I'm not going to discuss that. But because I, just like with the title, I couldn't leave things well enough alone, I came up with an alternative as well, which was this one, which was intended to be a satirical joke on the state of the science. But I got in big trouble with DOE because of this bottom thing. And then many years later, it just kind of disappeared after that. But many years later, I'm at an AGCI meeting, and Steve Schneider's giving a talk at the Wheel Auditorium, which was the Walter R. Roberts talk, and he shows this graph, and he didn't know where it came from. And it was something I'd done just for fun, and it showed up in other places as well. It's had a life of its own. Whoa, what's going on? So it's had a connection with AGCI in the process. Let's go into the real talk. after all this time. So if you look at the challenge of climate science and where we need to go to the future, it's important, and this is going to repeat some things that Jerry and others have already said. It's very important that we now make that connection between the science to impacts to societal needs to adaptation and mitigation. And something that just, that highlights that is if you look at the billion-dollar weather climate disasters in the U.S., every part of the country has been affected by those, and there's an increasing trend in those events as well. So it's leading to a significant cost already on the taxpayer, and yet most people don't realize this, that climate change is already having a significant impact upon them.
You have to be in Texas to understand that climate change is occurring.
Yeah. Well, speaking of Texas, there's been a lot of studies now that are starting to show that, that we're able to not, in the past we would just say, well, we can't really make the connections between science and an individual event. Well, now we're doing that. And in fact, the heat wave and drought in Texas was in 2011 is a clear indication of that, where it was the highest temperatures connected with the worst drought that the state had ever seen. And this just shows the number of 100-degree days in Texas and Oklahoma during that period. And the analysis showed that that event was about twice as likely to have happened because of the fact the background climate has changed. Well, we know that as part of this challenge, impacts are already occurring. For many impacts, the magnitude and the rate of change increases with human emissions. This is a graph from Catherine that deals with drought, but I won't have time to explain. Our civilization is built upon the assumption of a stable climate. But unfortunately, that's not what's occurring. And as a result, we're starting to see more and more of these kind of impacts, as I was talking about. So for many sectors and regions, failing to account for climate change in future planning will give the wrong answer. And yet, as Catherine and I just did, we did an analysis of all 50 states in terms of how well are they meeting FEMA's guidelines for an assessment of for planning, how the state will respond to disasters and plan for disasters. All but a few states do not include climate change in their analyses at all. So it shows we have a real problem. So we need to improve this two-way flow of information between the science and policy. Projected climate change at the spatial scale of impacts and decision-making is an important part of that. We need to get down to that urban and state level to be able to really meet those needs. We need the interaction between sectors, we know is already important, water and energy being an example of that, and between decisions and impacts on human society and ecosystems. And finally, the interactions between climate change and other stresses and local changes in natural variability are also extremely important. It's important for us to recognize that climate change is just one of the many stresses affecting the policies that need to be considered. So as I thought about the climate science and where we're heading for the next range of assessments, I just completed 4 different assessments. I was involved in IPCC, the National Climate Assessment, the WMO-UNEP ozone assessment, stratospheric ozone assessment, and then a special report that was done between the National Academy of Sciences and the UK Royal Society. And so I'm kind of in this in-between period before thinking about what we're going to do next, and how do we sustain this process. What are some key things? And Sherry touched on some of these already. We need to take the climate modeling down to the regional scale. So we need much higher resolution Earth system modeling than we've had up to this point. We're starting to get there. As was mentioned earlier, we're now running, Jeff mentioned this, we're now running at 25-kilometer resolution. And we're doing that on the petascale machine at NCSA at the University of Illinois in a study I'm doing with Warren Washington. We need better downscaling to make use of that to get it even down to further scales. We want to get down to hundreds of meters at the city level to really look at urban effects. Severe weather events is another very important issue, and I'm going to touch on some of those aspects in a few minutes. And then finally, I just thought I'd touch very shortly on sea level rise. So if we look at the climate models, the big need now is for both higher resolution and better science. There's always this challenge that goes on between climate modelers as to which one should you put your emphasis in, and they fight with each other about what we should be doing. We need to do both, but clearly there's a lot to be gained by going to higher resolution in the near term. And the fact that we're able now to go to petascale, and we're even beginning to take the codes and say, well, how can we plan for the next generation of exascale machines, 1,000 times faster, which will be available towards the end of this century. We'll be able to do the higher resolution while the physics and the chemistry and the biology and the models continues to develop. So, but we don't want to forget those things. We need to make sure that all aspects of the science are improved, and I'll touch on a couple things very shortly, and not to the level that I can in a 15-minute talk. Oh, this got slid over in an incorrect way. Well, if you looked at the last IPCC assessment, we were doing on the order of 1 to 2 degree resolution. For the next assessment, we need to get down to 1/4 to 1/2 degree to really meet those regional scale kind of answers. That doesn't mean every model is going to do that, but there will be model calculations, I think, at that level. The regional scale, likewise, analysis, the downscaling needs to be greatly improved, and we're hoping even to get some of these down to the order of 1 or 2 kilometers. But the problem with statistical downscaling at that level is the lack of enough measurements to really be able to do that. At the next level, I think we're going to begin to start seeing cloud resolving models that are also going to greatly improve, hopefully, our analysis of climate effects to finally begin to resolve this major question about aerosols and clouds that we've been dealing with for the last 25 years and longer. That was one of the first issues we talked about at the AGCI meeting 25 years ago. Going to climate extremes, heat waves are, and this is all based on the US National Climate Assessment, heat waves generally increasing, they're likely to become longer and severe. Cold waves are decreasing. Those things we understand pretty well. More precipitation is coming as larger events, and we expect that to also continue, that when you do get precipitation, it's likely to be as a larger event. A warmer atmosphere holds more water vapor, so again, it's not too surprising. And it's something we, again, fairly well understood. We'll talk a little bit about floods and droughts in a second, and hurricanes, and then I want to talk a little bit about tornadoes, if I have time.
We've got about 4 minutes with an adder.
Okay. If you look at droughts, there is no strong national trend, but there's increasing trends in some parts of the country. We expect those trends to kind of continue. I won't go into some of the physics behind that, but and certainly with floods. We're seeing more floods in certain parts of the country, particularly the Midwest and the Northeast. And we expect that to also continue. And for those regions, it's in part because of this increasing precipitation in general, but more of that precipitation coming as larger events. We don't have as firm an understanding of floods and droughts as we do temperature and precipitation extremes. But there's a lot of work going on in that area. Turning quickly to hurricanes, we have seen an increase in understanding of hurricanes being more intense, particularly in the North Atlantic. A very high resolution study that Michael Weiner at LBL did showed using the CSM, using the chem model with fixed sea surface temperatures from CMEP5 runs, shows that the model can represent the climatology of hurricanes quite well. And from that study found that they're likely to have fewer hurricanes, but the strongest storms will likely be more intense, which goes along with some other thinking that's appeared in the literature but it's substantiated perhaps for the first time with this very high resolution model. Turning quickly to thunderstorms, tornadoes, we just do not have a good firm understanding of how they connect with climate at all. There's been some data showing an increase, but we think that's more likely due to, in the number of tornadoes, but it's more likely that that's just due to better detection methods than anything. However, we do know from studies by Jeff Trapp and others that the tornadoes tend to be connected with two particular factors, vertical wind shear and available potential energy, and that if we then do analyses looking at how those might change in the future climate, there's suggestion that we're more likely to have a higher frequency of days with high CAPE and the right amount of wind shear to likely lead to more intense organized thunderstorms. But the jury's still out. And so we're actually initiating, Jeff and I are initiating a number of new studies to really look at this question, not only about how hurricane intensity might change, but also how the area of I said hurricanes, tornadoes might change, but also the area of tornadoes in the US might change over the coming decades. We did a study as part of 4 different workshops that were done for the National Climate Assessment to look at severe weather events and our ability to detect those events versus our understanding of the causes and how they relate to climate change in particular. And there's some things we can do pretty well, but there's things like tornadoes we still don't have enough knowledge on, but we're trying to work hard to improve that. Sea level rise, the key thing there to understand the changes over this century are going to be what's happening in Greenland and Antarctica, and I won't have time to touch much on that. And finally, just looking at the next US National Climate Assessment, the next generation of models and analysis will likely be much further advanced. That's going to help us to be able to do this transition of how we go from the science to the impacts. I'm hoping that we'll be able to use things like GIS to be as one of the tools towards being able to greatly enhance that. And I think we'll likewise have a much better understanding of extreme weather events and a changing climate by the time of the next assessment. And I thank you.
Okay, so any immediate questions for Don before we go to kind of more general? Yeah, go.
A lot of discussion about extremes is about extremes within roughly the climate that we know. What's your take on the tipping points or the idea of maybe it's really extreme climate change, potential climate change to put us in new situations where there are really fundamentally new things, not just slightly more intense hurricanes, but hurricanes where they didn't used to be. What's your take on that kind of thinking?
Yeah, I think, well, we're just not there yet. And that's, as I said with tornadoes, we don't really know how the area of tornadoes might change, and they could change substantially. I think that's somewhat true also of hurricanes. But the problem is really understanding those connections between sea surface temperatures and hurricane development that we still don't have a very good handle on towards getting there. Yeah. Marty?
Yeah, the climate change deniers or proponents like to make an issue of the so-called plateau, the fact that the running average climate has not changed very much in the last decade, and you do see that in the data. And what I'm wondering about is whether we have had any change in extreme weather events. See, I think you could probably explain that in terms of heat going into the ocean.
Oh yeah. There's been a lot of studies.
But I
now.
think,
Yeah.
but I'm wondering if that is causing a kind of stagnation or a halt to changes in other climatic events rather than global temperature. In other words, are we getting increased droughts or decreased droughts during this period when the global mean temperature seems to be stable?
Well, we don't have a firm handle on things like droughts, but we do have a firm handle on severe precipitation events. And we've definitely have seen a significant increase in the last decade in parts of the U.S., particularly Midwest and Northeast, in such events, but almost all the country being affected by more precipitation coming as larger events. But that's also, you know, the slowdown did not happened with temperature, but it did not happen with other aspects. The glaciers are still melting, the sea level is still rising. There's a lot of other aspects of the climate system that show that, you know, the climate is still largely changing.
I think on this particular question, I think what would be interesting to understand is, and we know that this plateau might be related to the tropical ocean, lack of El Nino, etc. At the same time, we saw in the Philippines and near Asia, those hurricanes that were stronger than ever recorded. And the question is there a relation between the two or not? I don't know, but
Yeah, we don't know that. Yeah.
All right, so let's declare the floor open for any of our speakers. Danny?
So you touched on planning for exascale computing and this notion of, you know, upping the resolution until we can max out the machine that we're going to have. And that's
But that's not really the idea. The fact is the machines make us available so that we can look at the higher resolution that we know we need to capture regional behavior. You know, one of the things that's going on, John Christie got brought up earlier this morning. John is out there right now publicizing analyses saying, well, the models do a very poor job in representing the change in temperature that has actually occurred in American cities. And you go, well, wait a minute, the models aren't even intended to do that analysis. Why would you expect that? But he uses that as a way of pointing towards, well, why you shouldn't believe in climate change, you can't trust these models, blah, blah, blah. But we do need to be able to get down to better regional behavior because that's what the people who do impacts analysis really need. And that's, so those new machines just make it possible for us to finally reach that capability.
I do think it's an interesting question for this sort of cross-disciplinary community as to what the best use of that type of computing resource really is. There are large uncertainties. For example, alternative forcing futures for all different kinds of forcings. We've not even nearly explored one of the attractors for the current generation of climate models, and that type of computing power would enable us to do so.
Yeah, I agree.
And maybe that might help policy support more. And it almost seems to me as a meta decision problem. Should we invest so much in maxing the resolution out, or what's the greater benefit to humanity? I don't think.
Well,
it's
there's a
clear-
lot of questions, and I was trying to refer to that earlier. Jerry could very much speak to this. We know there's a lot of improvements to be made in some of the physics and chemistry and biology in the models and how we represent various processes. As we learn more and be able to do that, that's an important priority as well. But does that become the dominating factor as you look at this computing time? I don't know. It's pretty clear that high resolution is going to improve a lot of things.
I want to
I
give
just
Jeff a
wanted to say
chance.
this is a debate that's a long-standing debate, and
Yeah.
it really comes down to sort of at a minimum three axes. One is resolution. You use that computational resource to go to higher and higher resolution. The other one's complexity. You start putting in more and more processes that you feel are important. And then the third one is ensembles. You
Yep.
use the resource to just run massive amounts of ensembles.
I have a slide that shows that 3D aspect, and I didn't include it here.
So those three communities, or the people that represent those communities, are constantly arguing their positions on, okay, a new computer, more resource, how do we spend that resource? The battle is always, essentially those three factors that come into play, and essentially it's a compromise. You don't just use it all for high resolution. You use it, you'll partition it amongst those three factions.